Recording's rolling. It is Friday, October 24. So you guys should turn in your gravitation and circular motion puzzles. So I was planning to do a few more of these for the guys today, but I think we've actually done enough of these. All right, so we've done enough. You just go ahead and turn in whatever we've done in class so far, along with your work, and then I will put those points in the grade book for you. And so what we'll actually do today is just conclude on satellite motion. And you guys remember I gave you guys a take-home quiz a couple days back, so that one's due on Monday. Right, we're on the special pep rally schedule, so yeah, fun times. Yeah,
Whenever I did this, I always did my work on a separate sheet of paper.
right? Yeah, that worked. All right, here we go. All right, orbital speed of a satellite in low Earth orbit. Start with some trivia here. Do you remember how fast? Oh, yeah. I think it's how fast worked out to about 7,900 meters per second. Yeah. So here, where that comes from. Here, give you guys a review. Actually, you know what? I think I have a poster to that one too. Yeah, it's right here. It's right here. Yeah, so if a satellite's going around a planet, okay. Now it's in low Earth orbit, so that's so close to the planet that it's just above the atmosphere. So the radius of the planet is basically the distance of the satellite, right? I mean, it's off a little bit, right? So the gravitational force, which here's the universe gravity from that, right, provides the centripetal force. Now the mass of the satellite, this is lowercase n, that cancels out. If you solve for the speed, you get this expression. And so you got 6.67 times 10 to the negative 11 here. The mass of the Earth in kilograms is 5.98 times 10 to the 24. The raised here is 6.38 times 10 to the 6. Okay. You put that all in. Here, I will feed this all in the calculator so you guys can see it actually work out. 6, so 10 to the negative 11. Oops. 11 times 5, 9, 8, 10 to the 24 divided by 638 times 10 to the 6. Okay. There it is right there. Okay, almost 8,000 meters per second. So if you get a satellite going that fast, it will orbit the Earth. And points on the board. Speed of a satellite in circular orbit. As long as it's circular. Yeah, constant speed. All right, everybody getting that. So it's not speeding up or slowing down. As long as the orbit is circular. I got Talia, Gavin, Cole, Bruce, and Kai. Speed of satellite. What if it's an elliptical orbit? It's probably a little more realistic. Uh, yeah, that would also be true. Here, we draw this up for you guys too. Okay. So this poster is really talking about like circular type motion. But what if it was elliptical? So the speed was changing. Here's a I'll call it P for planet. Okay. What if you have something that's orbiting it and it looks something more like this, which is definitely more like an ellipse. You guys remember taking the string one day and made a look. Okay. You guys made that an ellipse in your heads. Okay. Uh, because the speed over here, do you think it's going a little faster or a little slower than normal? Yeah, slower. And over here it's going a bit faster. Right. Yes. Now, glance ahead. I've got some questions coming up because it's Kahoot from the past. It asks questions about energy. So there's different forms of energy. One form of energy is called kinetic, and that's like energy of motion. And there's another form of energy called potential energy. We'll be studying this next week. And that's like energy of position or height, or like in this case, distance from the planet. Right? And it turns out though that if you add up these different forms of energy, as long as the system is closed, which is it is in this case, then the total, well, for the satellite plus the planet, that would be a closed system. The total amount of energy stays constant, but see, potential energy, that's a huge height, that's a huge distance away from the planet, and a very slow speed. Right? So it has a lot of potential and very little kinetic, and vice versa over here, it has a lot of kinetic, very little potential. Right, so I think that'll pop up at some point later on today. Right. I got Spencer, Talia, Gavin, Bruce, Kai. Period of a satellite is defined as Yeah, the time to complete one revolution. Yeah, capital T time period. There you go. All right. Got Kaya and Spencer, Gavin, Bruce, Kai. The higher a satellite is, Ooh, one winner. One winner. Yeah, somebody be winning. Okay. So here, that's what I was just showing right here. Or saying, asked you guys were actually telling me. You're saying, well, when it swings by really close, it'd be moving really fast. And when it's very far away from the planet, I might say, ooh, like it's higher in the, uh, in terms of altitude, right? It would be going slower, wouldn't it? Right? So the speed is changing, right? So yeah, further away, the slower it's going. Right? And as the slower it's going, wouldn't that actually take it more time to go around? Right? So the blue and the yellow are opposite of what would be the case. But the only one that works is the red one. All right. Ooh, got Talia picking up points. Circle is a special case of a circle's a huh, category. Oh yeah, everybody got that. Yeah, ellipse. Okay. And so those two focal points you guys had to trace around the ellipse, if they were the same focal point, that would be the center of a circle. Okay. All right. So you guys know what parabolas are. Like if you throw something near close to Earth, it makes that parabola looking shape. Right. Uh, let me mention a hyperbola real fast because that's an interesting kind of curve too. Right. Um, but so here, if I have a satellite going around in circular orbit, maybe it's going some speed, stay in circular orbit with that constant speed. Then what if I fire the engines to speed up a little bit? Or maybe it starts taking this elliptical type path, right? Right. What if I keep firing the engines, just go faster, faster, faster? You guys think at some point it reaches escape speed and just like flies away forever? Right? Yeah, if it's going fast enough. Right? Now, this is curved a little bit. Right? And in fact, if you trace it backwards, if you just run it back the other way, it could follow this curve and maybe go something like this, where it actually kind of bends. Right? But it has so much speed that it'll never actually orbit the planet. Right? Or you could replace this planet with the sun, and this hyperbolic trajectory would be something that was coming from outside our solar system, right? Which we've seen three of those in about the last 10 years, right? You guys heard Oumuamua from like a few years ago, and there's one they call I think like 3I right now, so that's going through our solar system. Yeah, and they know it's coming from outside our solar system because it's on a hyperbolic trajectory. Like it's not actually in orbit around our sun. All right, got Kaya and Gavin, Talia, Bruce, Kai. Circular orbit of a satellite orbiting Earth is characterized by constant, as long as it's circular. Yeah, all the above. Yeah, speed and radial size. And guys, what type of acceleration are we talking about? It's a special kind of acceleration. Starts with a C. Oh, it's centripetal. Okay. It's being moved in a circle. All right. Bruce, Gavin, Kaya, and Talia. Kai. The fastest moving planet in our solar system. Ooh, what do you think? Yeah, the planet closer to the sun. Closer you are to whatever you're orbiting, yeah, you got a faster speed. Right, run the equations. All right. Nicholas, Kaya, and Bruce, Talia, Kai. Pluto takes a longer time to travel around the sun than Earth because, yeah, both those statements. So if you look at orbital speed equation, right, so far out that has a slower orbital speed. But if you look at the circumference of its orbit, it also has a further distance. Right, so for you put those two together, it's definitely going to take it way longer. Yeah, both the above. Object is placed exactly halfway between Earth and the Moon. The object will fall toward. Uh, Yeah, look at the Earth. Yeah, because the Earth is more massive. Here, I'll draw that one out. Draw it out here. So, you got here's the Earth, E for the Earth, and maybe the moon's like over here, and for the moon. If you go geometrically halfway, you get those. I got these 12 centimeters apart, so 6 centimeters. Bam, right there is exactly the midpoint. I think you're supposed to a little stick figure with a little astronaut helmet. If the Earth is pulling you to the left with some gravitational force, the moon's pulling you to the right with a smaller gravitational force because it has less mass. Ah, so you see your Earth's kind of fall towards the Earth. I see it. There you go. I got Kyan, Nicholas, Bruce, Kai, Talia. Projectiles fired vertically from the surface of the Earth at 10 kilometers per second. Yeah, the best answer is probably this one here. All right, so it's going to rise but eventually fall back. Okay. I should pick the red one. That might not be completely terrible because the speed would be consistent with that. Right? If you got it going 10 kilometers per second, but you would need to go on an angle so it could start revolving around the Earth. Yeah. It's just going to go back straight coming down. Now, next week when we're doing conservation of energy, we'll be able to derive what's called escape speed. So you guys see this 10 kilometer per second right here? If that got all the way up to 11.2 kilometers per second, it would be going so fast at that point that it actually wouldn't fall back. It would just like fly off into space forever. So hold on to that idea for next week. Spencer, Nicholas, Talia, Bruce, Kai. A vertically oriented rocket that maintains a continuous upward velocity of, let's say, real slow, like 2 kilometers per second. As long as it's constant velocity, maybe it has the engines firing, just keep going. Yeah. Okay. So a minute ago, I just said that the escape speed from Earth is 11 point something kilometers per second, and this is going way slower than that. Right, so how could that escape her? And the key here is that this continuous upward velocity. Right. So now the rocket would have to keep blasting its engines for that to be true. Otherwise, it'd be slowing down and actually would fall back to Earth. Okay? Right. But as long as the engines are on, yeah, it could just keep going away. You could like tie a rope ladder from here to Mars and just very slowly, rung by rung, right, yeah, like walk off the Earth that way. Right? Yeah, so you can still escape Earth. All right, even with less than escape speed. Cole, Bruce, Talia, Nicholas, Kai. Early bird communication satellite hovers over the same point on Earth indefinitely. Huh? How would that happen? Yeah. Ooh, okay. A couple winners there. Figure this out. It's called a geosynchronous orbit. Okay. Here. So say I have the Earth right here. Okay. There's actually a radius you can calculate. It's somewhere way out here. Okay. Where the orbital time period would be 24 hours, and the Earth also takes 24 hours to rotate once. So if you were down on the surface of the Earth, let's say down the equator, really this would work right above the equator, and you look, or pretty close to it, you look straight up into the sky. Maybe you see that satellite. Maybe through your telescope, you see the satellite. Okay? And it would look like it's the same point in the sky, just traveling like all day, all night, right? All the way around, like the satellite never moves relative to you at the surface. Okay? Because both take 24 hours to go all the way around. Okay? Yeah, so that can be a useful place to park different kinds of satellites. Got Cole, Bruce, Talia, Nicholas, Kai. How long will it take for a satellite in low Earth orbit to make one revolution? Yeah, yeah, there you go. All right, so you guys remember that one. It takes about 90 minutes. Yeah. If you're the International Space Station, yeah, you see a new sunrise every 90 minutes. I got Nicholas, Cole, Bruce, Talia, Kai. How long would it take a satellite as far away as the moon to orbit the Earth? Yeah, about 20 days. Because doesn't the moon take about that long to go around? About 28 point something days to go around? Yeah. So any satellite that's that far out, has that distance away from Earth, take that time to go around. That's it. Now, Spencer, Talita, Cole, Bruce, Kai. Compared to a satellite in orbit close to Earth, the time period for a satellite far away from Earth, huh, yeah, it would be longer. Right, so take the last two questions and put them together. Right, low Earth orbit, say International Space Station, takes 90 minutes to go around. The moon takes 28 days. Yeah, that's definitely more time. Yeah, right. And actually, that has nothing to do with the mass of the satellite or the moon or anything like that. It's just how far away from the Earth. Yeah. Talia, Spencer, Cole, Bruce, Kai. Where does a satellite in elliptical orbit, oh, here we go, have the greatest kinetic energy? So that's energy of motion. Another way to say that is, where does it have the fastest speed? That also answers the question. Yeah, at the closest point to the planet. Right. Right. Going the fastest has the greatest of that kinetic type of energy. Uh, what remains constant in an elliptical orbit, say between the satellite and the planet? Yeah, it turns out total energy. Yeah, so we haven't actually covered this yet, but next week we'll start talking about this, which is that as long as you have a closed system, the total amount of energy stays constant. Right? So energy is not something that you can create or destroy. Now, energy can take different forms. It can take form of motion, that's called kinetic. It can take form of like location or height, it's called potential. There's some other forms too. You put energy in a spring okay. But yeah, the total amount of energy stays the same. Talia, Spencer, Bruce, Cole, Kai. Escape speed from the surface of the Earth. Yeah, all right. Some of you guys followed that earlier. Yes, I mentioned that earlier. About 11.2 kilometers per second. Okay. Now, what that actually means is that if the rocket was going that fast and you cut off the engine, so the engines aren't even blasting rocket fuel anymore, okay, at that point, it is going fast enough that it'll still be able to escape the gravity field of the Earth. Even if Earth's pulling back on it and trying to slow it down, yeah, it still has enough speed to break away. All right. Talia, Spencer, Bruce, Cole, Kai. All right, we're going for the win right here. For the win. Because the satellite is always changing direction. Ooh, an energy question. Does it lose energy? Yeah. So conservation of energy makes that false. All right. And yeah. Great segue to next week. So we got the bronze, Cole, silver, Bruce, and gold, Kai. All right, nice job, guys. And so, yeah, double check, make sure you got your puzzles turned in. And here, I'm just gonna roll some Vsauce videos until they call us for the pep rally.